Hello, I'm Alex Braylon, and today I'm presenting work I did with Omar Alonso and Matt Leese on how to measure inter-annotator agreement for all sorts of complex data. First off, let's review what is the point of measuring inter-annotator agreement. When we collect labels from workers, we assume that if the task is well-defined and objective, and the workers are capable and engaged, then mostly we should see the workers agreeing with each other on what the correct labels are. What we want is a quantitative measure of inter-annotator agreement that can answer these important questions, such as, is our labeled data set of high enough quality to be useful? Is the task well-defined and objective? Are the annotators reliable? Are the items being annotated too difficult or ambiguous, etc.? Let's take this very simple example of an annotation task where annotators are asked whether or not there is a penguin in the image. Here, 2 of the annotators agree that there is a penguin and 1 does not. That's what is called observed agreement, the fraction of label pairs that match. In the case of categorical labels, they have to match exactly. Now, to put that number in perspective, it's generally compared to what is called chance agreement, which is the probabilistic expectation of how many pairs would match simply by chance. So for example, for this categorical labeling task, any 2 labels might agree just by accident, which could depend on the prevalence of each category. And even bad data would still have some amount of expected chance agreement. So what we really want to know is how much better than the expected chance agreement is the observed agreement. And there are several measures in the literature that do this kind of comparison between the fraction of matched pairs observed versus fraction of matched pairs expected by chance. Now, our topic of interest is how about more complex annotation tasks? For example, here, the task is to caption an image, and the response space can be any free text input by the worker. This response space can be so large that any methods looking only at exact match will no longer work because you'll almost never get any exact matches. And there's a large variety of this kind of complex task. Annotators might be asked, for example, to rank elements in a list, translate a sentence between languages, draw multiple bounding boxes or key points in an image, highlight multiple spans of text in a document, produce syntactic parses of a sentence, or whatever else you can imagine. In our work, we conduct the first large-scale investigation that we know of across multiple diverse complex annotation tasks. In order to do this, we show that existing evaluation metrics for each task can be converted into distance functions for measuring partial credit rather than exact match. And these evaluation functions can then be used in combination with a general form of the inter-annotator agreement measure, Krippendorff's alpha. In doing so, we identified a key limitation of Krippendorff's alpha, which is its reliance on mean distances, which can then lead to mistakenly discarding good data. To overcome these limitations, we propose new inter-annotator agreement measures that compare distributions of observed and expected distances instead of their means, finding that this is a more reliable approach. Okay, let's start by talking about how we use Krippendorff's alpha. Krippendorff's alpha uses a distance function to compare labels instead of relying on exact match. And the distance function plugs in here to get the ratio of observed distances to the distances expected by chance. And this introduces us to one of the distinctive problems when measuring annotator agreement for complex data, as opposed to simple data. And that problem is the choice of the distance function. The basic requirements for a distance function are non-negativity, symmetry, and triangle inequality. So there's this generalized form of Krippendorff's alpha, and it's potentially very versatile, but we don't really know much about it, much about how well it works across various complex tasks, because there are only a couple of studies that have used it on complex tasks, very specific tasks, as opposed to really any cross-task studies. And so we want to know how well does this work actually in general. Now, one of our realizations is that for any given complex data set, chances are there's an existing evaluation function. And with minor manipulations, these evaluation functions can be adapted into distance functions to plug into the generalized form of Krippendorff's alpha in order to be generally applied across tasks. For example, here, when evaluating machine translations, Traditionally, this blue score is used, or for comparing ranked lists, people might use Kendall's tau. And these evaluation functions can be manipulated through inversion, et cetera, to make them into viable distance functions. To see this idea in action, let's start with a pretty complex task, translations. Here we have 3 Japanese sentences, and each one is translated into English by 5 workers. Now let's pick a distance function, say the glue score, which is related to the blue score that I just mentioned. And we'll measure distances between all pairs of sentences, with smaller distances representing better glue scores. If you look at this heat map, you see the blocks next to the diagonal being more purple, and those indicate that the pairs of translations of the same source sentence tend to have smaller distances. These are the observed distances, the distances between intra-item annotations. On the other hand, we see on the off diagonal a big orange space here. These are the expected distances for the chance correction term, which is estimated by comparing totally unrelated sentences. So if the workers were, for instance, writing sentences that were extremely different from each other, then their observed agreement would start to look more like the chance expected agreement. And with that, you have Krippendorff's alpha for this translation data set. So this raises a question that we did not have to answer for simple tasks where the distance function was a 0, 1 exact match. That question is, what should my distance function be for my complex task? There are usually a good variety of reasonable choices depending on the task. And so the question is, how do we choose one, and does it matter? Intuitively, if the data set is reasonably good, we want to see a distinction between the observed distances and the expected distances. In other words, the intra-item distances should look pretty purple and the cross-item distances should look pretty orange. And we can motivate this further by referencing this field of distance metric learning, where the goal is to learn a distance function that puts points with the same label close together while pushing away points that have different labels. Let's take this example and compare 2 distance functions. So the glue score, which I already introduced, and the blue score, which was its predecessor. And what we see pretty clearly visually is that the blue score is a lot worse at distinguishing observed distances from expected distances. It's a lot blurrier here compared to the nice crisp contrast between the purple and the orange for glue. And there's an important implication here, which is that the choice of distance function does matter. Because if you were to use an insensitive distance function like blue, relatively, your measured IAA score will be so low, possibly, that you might decide to blame the data and throw it away. Or conversely, you might accept data that's unreliable. But now we come to something odd that we observed while experimenting. And that is, actually, if you measure Krippendorff's alpha on this example, you do not get a higher score for the distance function that is visibly better. So why is that? Let's look at some hypothetical data. On the top here, we have a very overlapping pair of observed and expected distance distributions. And on the bottom, they're more clearly separated. Intuitively, this bottom shows better distinction between observed agreement and what should be expected by chance. Right? Less overlap should be a better agreement score. However, when taking the ratio of the means of these distributions, because the means are actually exactly the same, both cases yield the same value for Krippendorff's alpha. So the first problem we encountered with Krippendorff's alpha is that it can give an undesirable relative score when choosing between distance functions. And that's what happened when we compared the blue and the glue scores here. If you were to put the observed distances on the diagonal into the blue histograms and the expected distances into the red histograms, you can see that while there's much less overlap for the glue score on the bottom here compared to the blue score, the ratio of the means of these distributions doesn't really capture as much information as looking at these whole distributions. And there's actually another problem we found when applying Krippendorff's alpha to various complex data sets, and that is in its interpretation. So in other words, how do we use this number to decide whether the data is of good enough quality? Well, Krippendorff's alpha was largely developed for looking at content analysis tasks. And for this kind of data, the judgment by Krippendorff was that if the alpha is above 0.8, then it's good. Whereas 0.667 is the lowest conceivable limit, below which we're supposed to discard the data. Now, the caveat was this shouldn't necessarily be expected to hold for other kinds of data. And that caveat is correct, because here we have an example where plugging in the glue score for perfectly fine translation data yields an alpha of 0.35. And we certainly would not want to throw out this data simply because the Krippendorff's alpha was too low. So we proposed two distributional approaches to Krippendorff's alpha when applied to complex annotation tasks. And our methods, much like alpha, take a distance function to collect the observed and expected distances. But then rather than just take the ratio of the means of the distributions, we compare the whole distribution. So one of the proposals that we have is to apply a Kolmogorov-Smirnov test. And this is a test of whether the two distributions could be samples from the same population. We think this is a better way to answer the question of how different are our annotators' agreements with each other from what might be expected due to chance. And in our paper, we talk about another method, but I'll skip over that in this talk. Okay, so in our paper, we experimented on 7 data sets, but I'll just review 2 of them. For translations, we looked at the blue and the glue score, but also at a much coarser distance for strings, which is the Levenstein string similarity distance, which might be argued isn't really appropriate for natural language comparisons. And on the other hand, we also looked at a much more state-of-the-art neural language model, which is the BERT score. And we see that the Kolmogorov-Smirnov method we propose for comparing the distributions of observed and expected distances gives them scores that are in the right order. The Levenstein distance has the most overlap and the worst score. The BERT score has the least overlap and the best score. Meanwhile, we see that if we had used Krippendorff's alpha instead, the Levenstein distance would have looked counterintuitively better than blue or glue. Another data set we looked at was bounding boxes. And in this case, the favored evaluation functions are intercept over union, or the more recent generalized intercept over union. A cruder measure is to take the L2 norm between the box centroids. And this would ignore information about the height and the width of the boxes. And an even cruder method would be to take the difference in the count of the boxes given by annotators, this count diff here. So we would intuitively think that this is the worst, and then L2 is not quite as bad, but not as good as the IOU or GIOU. And again, we see that the KS score gives a reasonable ordering, whereas the Krippendorff's alpha surprisingly puts the L2 norm much higher than the standard measures. So in conclusion, our goal was to figure out how to measure inter-annotator agreement generally across all kinds of different complex tasks. This was a comprehensive study across 7 different complex annotation tasks using 24 different distance functions. In particular, we look at one existing inter-annotator agreement measure, Krippendorff's alpha, and learn how to use its generalized form together with distance functions converted from common task-specific evaluation functions. And we propose distribution-based inter-annotator agreement measures that give a better ranking of distance functions and a more complete picture of how different the observed agreements are from chance. Thank you for listening, and you can find the code for implementing our measures here at this address. Bye.